Welcome to Margin Notes, the podcast that digs deeper into the ideas that shape how we think. Today, we're exploring something that might just change how you see math forever. Not formulas or equations, but the hidden mental toolkit behind them. We'll talk about precision, problem solving, nonlinear thinking, decision-making, and the surprising power of mathematical thinking in everyday life.
You know, for so many of us, math class felt like, wow, a foreign country. Numbers and formulas lived in this abstract space, totally disconnected from the real world we navigated outside the classroom door. We calculated X, we graphed lines, all while wondering, am I ever actually going to use this? And honestly, for the specific calculations, maybe not every day.
That disconnect is incredibly common. We often feel like we can just discard the tools, the precise equations or algorithms the moment the test is over.
Right. But what if the real lasting value wasn't just in performing those specific calculations? What if it was in the thinking those calculations required? What if, buried beneath the equations, was a powerful way to process information, solve problems, and make decisions? A way of thinking we use constantly, even if we don't label it math.
That's exactly it. The procedural part might fade, but the underlying cognitive skills, the logic, the way of structuring thought, the analytical approach, those are transferable skills we apply everywhere, often without ever tracing them back to their mathematical origins.
And that's precisely the mission of this deep dive. We've taken this stack of source material that dives headfirst into that idea. It pulls the concepts usually hidden under layers of numbers and symbols and shows us the surprising, useful, and frankly, cool insights about how embracing mathematical thinking, not necessarily calculus or algebra, can seriously level up your analytical skills, boost your creative problem solving, and sharpen your everyday decision making. This is about thinking better for anyone, no matter your past experience with a calculator.
It's less about being a human calculator and more about cultivating a powerful way to see and interact with the world.
Yeah. Okay, so if it's not just crunching numbers, what is mathematical thinking at its core?
Well, the material describes it as a fundamental way of processing the world, not just procedural, but deeply theoretical, conceptual, and crucially, intensely practical.
I love the analogy it uses. Equations are like recipes. They're the tools, the methods you follow. But mathematical thinking, that's the skill of the baker.
Yes, exactly. The baker understands the ingredients, the techniques, the chemistry. They can pick up any recipe and use it effectively, adapt it, or even invent a new one because they grasp the underlying principles. Mathematical thinking is that same kind of transferable skill, the ability to apply the reasoning, the logic, the method to entirely new situations.
And it's fascinating because historically, math didn't start out quite so abstract, right? The source touches on how it began with a very practical needs trade, counting livestock, stuff like that.
Exactly. It was rooted in the tangible world. But then thinkers, particularly around 500 BCE, started using math to prove things they couldn't directly see or conceptualize, like forces or abstract relationships. It began evolving into this tool for exploring ideas beyond the purely physical.
And then, especially in the last few hundred years, it just exploded. The material notes how math is now really seen as the science of patterns, capable of exploring patterns in both the real and the purely theoretical.
That abstract capability is actually its great strength. It allows us to analyze intangible ideas, gravity, yes, but also economic trends, population dynamics, weather systems, complex networks, things that don't have a physical form you can touch or count on your fingers.
And the really freeing part is, you don't have to be a mathematician to tap into this power.
Not at all. Thinking mathematically helps you approach finding answers, break down daunting tasks into manageable parts, build stronger arguments, spot and correct your own errors, ask sharper questions, avoid making shaky assumptions, and recognize underlying patterns in data or situations.
Okay.
It makes your thinking more logical, more analytical, more robust. That's the takeaway for daily life.
Building on that idea of robustness, something that really stands out in the source material is math's unique strictness. This focus on precision. It's like a language, but a very particular one.
It is presented as a universal language, yeah. And while it shares the basic structure of human languages combining expressions into sentences, its rules are far more rigid than, say, English.
Right, expressions like 2 plus 2 are like phrases. You combine them into equations. The sentences like 2 plus 2, 4. And unlike a sentence in a novel, the goal of mathematical sentence is always to state something that is undeniably, logically true or false.
The only exception noted is open sentences with variables, which become true or false only once the variable's value is determined.
Which leads to that mind-bending concept of vacuous truth in conditional if-then statements. The example given is, if dragons existed, they would be pink.
It's fascinating, isn't it? Because the condition, if dragons existed, is false. The statement is considered vacuously true. You can't disprove it because the premise itself is unfounded.
Right, you can't test it.
It contrasts sharply with the statement that is simply false because the condition is met but the outcome isn't true, like if it is morning, I am drinking coffee, if you happen to skip coffee that morning.
Yeah.
Math doesn't allow for that ambiguity. It's strictly true or false, or, in the case of vacuous truth, true by default of an impossible premise.
And that strictness highlights just how full of ambiguity English is. The source gives some incredibly relatable examples.
Oh yeah, the CDC headline, one is stark. One person dies every 36 seconds. If you take that literally, it's nonsensical.
Right.
It implies a person dies, then somehow resets, only to die again 36 seconds later, endlessly repeating. We intuitively understand the statistical intent, but the literal phrasing is absurd.
Or the classic road trip confusion, turn here, left, right.
Exactly.
Are you confirming the direction or agreeing that the speaker is correct? English relies so heavily on context, tone, and shared understanding, which makes it flexible, but also ripe for misinterpretation.
Even seemingly simple things like synonyms and antonyms differ. In math, you can express 10 as 2 plus 2 plus 2 plus 2 plus 2, but the system prefers the most concise form, 10.
Yeah, simpler is better.
English, however, offers a vast array of near synonyms, each with subtle nuances in meaning or connotation.
And negations, the antonyms. In math, the negation of a true statement is definitively false, and vice versa. It's a clear, unambiguous opposite.
But try negating all memoirs are boring in English. It could mean not all memoirs are boring, suggesting some are interesting, or some memoirs are exciting.
Right, there's interpretation.
Both are valid negations if the original is false, and our interpretation is colored by our own experiences and biases.
So while English's flexibility is its artistic strength, math's demanding precision, as the source points out, actively works to prevent the misunderstandings built into our more fluid language.
Learning to think with that kind of precision, even when not using numbers, can make your own communications significantly clearer and more purposeful.
Yeah, I can see that.
It helps you spot the kinds of reasoning errors the source mentions, like synonym errors where you subtly swap definitions, or non sequiturs where the conclusion doesn't follow the premise, or red herrings that distract from the main point pitfalls that often arise from a lack of precision in language and logic.
Okay, so if mathematical thinking is this precise baker's skill, how do you actually build it? It sounds like it's not just about being instantly right. It's a process involving trial and error, like mastering any skill.
It absolutely is. The material breaks down this process into 4 key steps that mirror how discovery happens not just in math, but in many fields: specializing, generalizing, conjecturing, and convincing.
Specializing sounds like focusing on a specific example, like getting concrete.
That's the first step. You take a general idea or a potential rule and test it out on specific concrete examples. The Black Friday tax and discount example from the text is perfect for this.
Okay.
You have a $1,000 laptop, a 30% discount, and a 10% sales tax. Does it matter if you calculate the discount or the tax first?
Okay, so you specialize by trying it both ways. $1,000 minus 30% discount is $700. Add 10% tax on $700 at $700.
Right.
Total $770.
Right. Now the other way. $1,000 plus 10% tax is $1,100. Apply the 30% discount on $1,100, which is $330. $1,100 minus $300 is, oh wow, still $707.
They're the same. And the source suggests you wouldn't stop there. You'd test this with a different price, different percentages, using more examples to specialize and build confidence that this wasn't a fluke.
And that evidence from specializing is what allows you to move to generalizing.
Okay.
You take the outcomes of those tested examples and form a broader rule or understanding that you believe applies universally in this case, concluding that the order of applying a percentage discount and a percentage tax doesn't change the final price.
So specializing provides the data, and generalizing is forming their hypothesis based on that data. What if you don't have a clear rule yet? Like you're just guessing?
That's where conjecturing comes in. It's making your best educated guess, forming a hypothesis when the answer isn't immediately obvious or provable in every single case. It's like the legal principle of not guilty until proven otherwise.
The source mentions Goldbach's conjecture, that every even number greater than 2 is the sum of two prime numbers. It's been tested for literally billions of numbers and holds true. But because you can't possibly test every even number into infinity, it technically remains a conjecture, not a proven theorem.
And it's important to remember that it's perfectly okay if your initial conjectures are wrong. The value is in the process making the guess and then testing it, because that testing process itself reveals new insights and helps you refine your understanding.
Okay, that makes sense. So once you feel you have a solid conjecture, tested through specializing and generalized into a potential rule, the next step is convincing.
This is about presenting your tested idea to others. The practical advice given is to start with someone you trust, who will likely be supportive, which helps you articulate your thinking.
Get your thoughts straight first.
Exactly. But then, crucially, seek out a skeptic, someone who will rigorously challenge your work.
That sounds uncomfortable, but I can see how the pressure of defending your idea against a critic would force you to think through it more deeply and reveal any weaknesses. It's like the peer review process in science.
Precisely. That challenge makes your final idea stronger. And a key insight mentioned from John H. Mason is the importance of writing everything down during this whole process. Your initial thoughts, your steps, your frustrations, even the mistakes.
Really? Even the mistakes?
Yeah, that documentation isn't just for others. It helps you structure your own thinking, aids the process of generalizing, and provides material for self-reflection.
The 9-dot puzzle, where you have to connect the dots with only 4 straight lines without lifting your pen, is a great illustration of this process, especially the conjecturing and how assumptions can block the solution.
Oh yeah, that one's classic.
Thinking the lines must stay within the grid is a common, limiting conjecture that needs to be discarded to find the solution outside the box, a sort of generalization about the rules.
It forces you to question your initial assumptions, which is fundamental to effective problem solving.
And these mathematical thinking skills don't operate in isolation, do they? The source highlights how they work in concert with several other cognitive processes, like they have buddies.
That's right. They have companions. First up is analytical thinking.
That's the process of breaking things down into smaller components to understand them individually and find differences or specific problems within them. It's the core of problem-solving skills, right?
Pretty much. But if you get stuck just focusing on the pieces, you can end up with analysis paralysis, losing sight of how they fit together.
Right. Seen that happen.
That's where synthetic thinking complements it.
Synthetic thinking is about finding patterns and similarities across those different pieces you've broken down, understanding how they work together to form a whole.
So analytical thinking finds differences. Synthetic thinking finds similarities and connections. The example given is analyzing consumer data for a Dodge truck ad campaign.
Okay.
Analytical thinking breaks down preferences, engine power, being American-made, family needs, while synthetic thinking combines these insights into a unified, compelling message.
Building on that is systemic thinking, which sounds like it takes that synthesis even further into understanding complex relationships.
It's presented as a technique for managing multiple interacting elements by viewing them as a cohesive whole system. The source outlines a 4-step process. List components, group similar ones, find the common theme across those groups, resulting in a hierarchy from individual components up to a common theme.
So it's leveraging both analytical, listing, and synthetic grouping and theming approaches within that systemic framework. Got it.
Then there's critical thinking.
This involves analyzing facts, organizing ideas, forming opinions, and drawing conclusions based on logic and evidence. Standard stuff, you'd think.
It's vital for evaluating information and forming reasoned judgments. However, the material is careful to point out that critical thinking is not suitable for purely intuitive or emotional decisions, like choosing a romantic partner or deciding your favorite color.
Right, it has its limits.
While it acknowledges emotions, it emphasizes the need to not be controlled by them, citing things like how unreliable eyewitness testimony can be compared to more objective forensic evidence.
And it contrasts this with mathematical thinking. While math seeks to prove hypotheses true or false using rigorous methods, critical thinking is more about interpreting information, evaluating different perspectives, and forming well-reasoned opinions. Critical thinkers, according to the source, are good at judging sources, identifying assumptions, defending their position with logic, and asking probing questions.
The Heinz dilemma example is a classic illustration. Should a man steal a drug to save his dying wife if the pharmacist is price gouging?
Oh yeah, I remember that one.
Critical thinking involves weighing multiple complex factors: the value of life, the ethics of stealing, the pharmacist's actions, the nature of capitalism, without expecting a single true-false answer.
And finally, creative thinking. This feels different.
This is the divergent part, generating novel ideas, using imagination, especially when you're stuck. Math is often convergent, narrowing down to a solution, while creative thinking is divergent, exploring a wide range of possibilities.
But they're presented as working together. A creative leap can generate a wild hypothesis or a new approach that mathematical thinking can then take and test rigorously.
Exactly. And it adds that simply engaging in creative activities have health benefits.
Notice.
It shows how these different modes of thinking aren't isolated silos, but a connected toolkit.
Speaking of modes, the source goes into detail about the brain's two primary learning modes, focused and diffuse.
These are fundamental to how we absorb and process information. Focused mode is that intense, concentrated attention you use when directly tackling a problem, like shining a tight spotlight.
Laser focus.
And diffuse mode is a more relaxed state, where your subconscious is working in the background, making connections more broadly, like a wider, softer beam of light.
Okay.
Effective learning often involves alternating between the two. You use focused study to initially grasp concepts, then allow your brain to process in diffuse mode during breaks. That's often when insights click and you have those aha moments.
And not using diffuse mode can lead to the Einstellung effect, getting stuck on the first idea or method you try, even if it's not the best one, which blocks you from seeing alternative, potentially better solutions.
The 9-dot puzzle is, again, a perfect example. The Einstellung is assuming the lines have to stay within the imaginary box of dots.
Right, the first wrong assumption.
Focusing only on the procedures you already know can foster this effect in math, preventing you from seeing a simpler or more effective approach.
So taking breaks isn't just loafing, it's actually crucial for learning, like neurologically important.
Absolutely. It allows your brain to switch into that diffuse mode, which is essential for building a deeper understanding and making those broader connections between ideas. It's like needing rest days for muscles after exercise.
And the source offers practical tips for triggering diffuse mode. Sleep, especially REM sleep, is incredibly powerful for consolidating learning and processing problems. Thinking about a problem before you go to sleep can even direct your subconscious processing.
And engaging in mundane tasks works well because they require just enough attention to keep you from getting bored, but not so much that they engage focused thinking. Walking, showering, doing dishes, these are classic diffuse mode activities.
Just don't binge watch TV.
Right, avoid tasks that pull your focus elsewhere, like binge watching something complex.
It also talks about chunking, how our brain naturally groups separate bits of information into meaningful units or chunks that are easier to recall and apply.
Think of it like creating a zip file or organizing files into folders on your computer. You take raw data, identify the key points, and then connect them into a single usable concept.
And you can chunk from the bottom up, using examples and details to build the concept, like specializing, or top-down, understanding the big picture first and then fitting the details in, like generalizing.
Yeah, both ways work, but the source highlights a crucial pitfall here: the illusion of competence.
Ooh, what's that?
This is thinking you understand something just because the information is available to you in your notes, in the book, or searchable online, versus truly understanding it because you can recall it from memory and apply it.
Oh. Just because I can look it up doesn't mean I know it.
Exactly. Recalling information from memory, especially after you've let your diffuse mode work on it, actively strengthens those neural connections and builds robust chunks much more effectively than just rereading notes or looking up answers.
So practicing recall, maybe soon after learning something or before sleep, helps solidify those new chunks. Makes sense.
Definitely.
Shifting gears slightly to how we often perceive the world, the source points out our intuitive bias towards linear reasoning.
This is the simple idea that if something is good, more of it is proportionally better. The example used is hunger. 1 sandwich is good, 2 might be better, 3. Uh-oh.
But as it notes, this ignores diminishing marginal utility. The 3rd sandwich doesn't add the same value as the first one did. It might even make you feel worse.
Linear thinking relies on 2 principles: additivity, where the combined effect of multiple things is just the sum of their individual effects, like two oxen pulling a load, and homogeneity, where the output is directly proportional to the input, like assuming paying double for a bottle of wine makes it exactly twice as good, which it usually doesn't.
Yeah, definitely not always.
The source gives great examples of how these fail in reality. Garden fertilizers, for instance, they can interact chemically, so the combined effect isn't just adding up what each does alone.
Right, they could cancel each other out, or worse.
Or trying to scale up production of imported goods. Costs, demand, and market saturation don't simply scale linearly with how much you import.
The core problem is that linearity doesn't account for feedback, how an action changes the system or environment, and how that environment then responds over time and space.
So why is linear thinking so common? It's intuitive, it's easy to understand, it fits simple cause and effect models, and it works well with traditional quantitative methods. It's simpler.
And to be fair, linear models are useful for certain everyday decisions. The text uses the example of comparing phone plans based on cost per megabyte.
Yes, you can set up simple linear equations, YMX plus B, for the cost of each plan based on data usage. Find the crossover point where they cost the same, and then use that point to decide which plan is cheaper based on your estimated usage. The source walks through calculating that specific crossover point for example plans.
So, below a certain amount of data, one plan is cheaper, and above it, the other is. It gives you a clear breakpoint for decision-making. Useful.
But the overwhelming reality of the world, as the source emphasizes, is nonlinear, where the output is not directly proportional to changes in the input. Historically, science often simplified models because nonlinearity was much harder to analyze and understand.
And applying that intuitive linear thinking to a nonlinear situation can be genuinely misleading, even dangerous. The Swedish conundrum example is particularly striking.
It describes how a simple linear graph might suggest that as a country becomes more Swedish, more welfare spending, its prosperity goes down, and vice versa for the US.
A straight line going down.
But a more accurate nonlinear view, perhaps a bell curve, shows both countries might be moving towards an optimal middle ground, just starting from very different points.
Meaning that in complex systems like economics or politics, the right direction to move often depends entirely on where you currently are on the curve, not just a simplistic more is always better or less is always better.
Exactly. Another powerful example is linear regression, predicting that all Americans will become overweight or obese by a certain future date.
I've seen headlines like that.
By blindly projecting a straight line based on past trends, you get an impossible outcome, over 100% of the population. The real-world trend is a curve that naturally flattens out below 100%.
The source highlights the fundamental error there, assuming a constant rate of change, which is only true in purely linear systems.
Recognizing that linear bias in our own thinking and actively training ourselves to look for and understand nonlinearity is crucial for making sense of the complex world around us. It takes effort.
Diving into another area where mathematical thinking is key: probability and risk. The source kicks this off with a fun origin story about lotteries in Genoa, Italy.
Yes, they started as bets on who would be elected to the Senate, then evolved into betting on numbers drawn by chance, which is the basis of modern lotteries. Kind of neat.
Which is a perfect example of the blend of probability and risk. Low probability of winning means high risk, but that's balanced by the potential for a high reward, which is the hook, right?
That's the lure. The material analyzes a simple lottery. 10 million combinations, $7 million prize, $1 ticket. Spending $10 million guarantees a win, but you lose $3 million overall.
Ouch.
Buying 2 tickets gives you a 2 in 10 million chance, not 1 in 5 million. And spending 7,001 apart guarantees you a loss, as the maximum payout is $7 million.
So simple math shows it's usually a bad bet. And this is where the concept of expected value becomes so useful.
Expected value is a mathematical concept that helps you quantify the long-term average outcome of an event that involves chance. It goes beyond just the probability or the risk in isolation. It gives you a clearer picture.
The roulette example illustrates it well. A $1 bet on black. There's an 1837 chance of winning $1 since there are 18 black numbers, but a 1937 chance of losing $1 due to 18 red and the green 0.
Right. To calculate the expected value, multiply the value of each outcome by its probability and sum them. 1837 $1 plus 1937 that $1 equals 0.027 cents.
Negative 2.7 cents.
This means over many, many spins, for every dollar you bet, you can statistically expect to lose about 2.7 cents on average. It quantifies why the house always wins.
Compared to the pig race example.
Yeah.
A $100 bet on one pig with a 10% chance of winning a $1,000 reward.
The expected value here is 10% $1,000 plus 90% $0 or $100.
Okay, so $100.
This doesn't mean you will win $100 on that single bet, but that over many repetitions of this exact bet, you would average $100 back per bet.
So if the cost of the ticket to enter this bet is less than $100, it's a mathematically favorable bet in the long run. If it's more than $100, it's unfavorable. Expected value helps you make that long-term judgment.
And this same concept is applied in real-world scenarios like car insurance. Insurance companies calculate your premium based on the expected cost of claims for someone like you,
which they figure out by multiplying the expected frequency of claims by the expected severity or cost of those claims.
Exactly. The source includes an example calculation using sample probability distributions for how often claims occur and how much they cost. It calculates an expected number of claims at 0.80 per year.
Okay.
And an expected claim amount at $18,375.
Wow. Okay.
Multiplying those together gives an expected total claim cost of $14,700 per year for that fictional driver. This provides the mathematical basis for setting the insurance premium.
Gotcha.
While those are made up very high numbers, it clearly illustrates the underlying concept insurers use. And the source includes an exercise for the listener to try recalculating with new numbers, which is a great way to apply the specializing principle we discussed earlier.
Finally, let's talk about testing your thinking might, which often comes in the dreaded form of tests. Ugh.
Tests often get a bad rap, but the source reframes them as valuable learning tools precisely because they force you to practice repetition and recall, which are crucial for building strong chunks of understanding.
It even suggests that the pressure of a test can enhance concentration and retention. I remember a specific fact from a high school history final years later, and I'm convinced it's because I had to recall it under pressure, like it burned it in.
That focused intensity can indeed etch information more deeply. And the source offers some practical, actionable tips for dealing with test anxiety, which is very common.
Reframing those physical symptoms, the pounding heart, sweaty palms, not as pure terror, but as your body getting ready, like being anxious to do your best, kind of like pre-game jitters.
Yeah, shifting the interpretation. And questioning the negative stories you tell yourself about failing. Practice mindfulness. Observe those fear-mongering thoughts without letting them control you.
Deep belly breathing is recommended to activate the calming parasympathetic system, something to practice before test day itself.
Good advice. And if possible, practice testing in a situation similar to the real thing, like a busy coffee shop if your test is in a crowded classroom.
Get used to the environment.
There's also a great test-taking strategy mentioned from Barbara Oakley. Hard things first.
That sounds counterintuitive. I always did the easy ones first.
It does, but the approach is smart. Scan the entire test first to identify the hardest problem. Spend just a few minutes on it, maybe 2 or 3 to get your brain started. Then, if you're stuck, move on to easier problems.
So while you're working on the easier ones, your diffuse thinking mode is subconsciously processing that harder problem in the background, like letting it simmer.
Exactly. When you return to the harder problem later, you'll often have a fresh perspective or a new approach available because your diffuse mode has been working on it. This strategy actively helps combat the Einstellung effect, getting stuck on one line of thinking.
And it ensures you make progress on the parts you do know, rather than getting bogged down early. That actually makes a lot of sense.
For multiple choice questions, the tip is to cover the answers first. Read the question carefully. Try to formulate your own answer before looking at the options.
Okay.
Then uncover the options and see which one best matches your own answer.
That makes sense. It prevents you from being misled by plausible-sounding wrong answers that might distract you if you saw them first. Good tip.
So the key takeaways about tests. Get enough sleep. View them as allies that help solidify learning. Use the hard things first strategy. Practice reframing anxiety, and use techniques like covering answers and double-checking to avoid the Einstellung effect.
So, wow, we've really come full circle, haven't we? From that initial feeling that math class was just pointless procedures, to uncovering this incredible toolkit of thinking skills underneath.
Absolutely. Precision in language and logic, that iterative cycle of specializing, generalizing, conjecturing, and convincing. Understanding how analytical, synthetic, systemic, critical, and creative thinking work together, leveraging the brain's focus and diffuse modes, navigating a world that is fundamentally nonlinear, and using concepts like expected value to understand chance and risk. It's a lot.
These aren't just abstract concepts for academics or engineers. They are practical, powerful tools for navigating the complexity of the real world, breaking down problems you face every day, making clearer decisions, and communicating more effectively in your own life.
They change how you evaluate information, approach challenges, and even understand your own learning process. Really fundamental stuff.
Maybe the most valuable equation isn't one written with numbers and symbols on a page that you have to memorize. Maybe it's the one you create yourself, by combining these different ways of thinking to tackle a problem unique to your own life.
That's a great way to put it.
Keep noticing where these ideas pop up for you.
Thanks for listening to Margin Notes. If this episode gave you something to think about, share it, leave a review, and subscribe for more deep dives like this. Stay curious. Stay sharp. See you in the next one.